Today we will be discussing our next experiment, that is auto rate fallback rate adaptation algorithm simulation for 802.11 AX channel. So auto rate fallback in short is also called as ARF. So you can find in literature generally the term ARF rate adaptation algorithm is widely used. So learning objective is to create a multi-user high efficiency format configuration object and initialize the transmit parameters for 11x standard. To configure TJX channel for 20 MHz bandwidth using TJX system object. To pass this transmit waveform through the TJX channel and add additive white Gaussian noise to the transmit waveform. And at the receiver, we do receiver processing like packet detection, simple timing synchronization, channel estimation, equalization, and demodulation. The main objective is we vary the modulation and coding scheme according to ARF rate adaptation algorithm. So before going into the code, let's discuss what an algorithm is. So ARF is algorithm, just introduction to the algorithm. The IEEE 802.11 standard does not define any standardized rate parameter rate adaptation algorithm for dynamically varying the modulation rate. The implementation of rate adaptation algorithm is left to the WLAN device manufacturers. ARF is an open loop rate adaptation algorithm, meaning there is no feedback from the receiver. I mean, the algorithm, the rate adaptation algorithm does not depend on the feedback of the receiver to the transmitter. ARF was the first rate adaptation algorithm to be published, and it was designed to optimize the application throughput in WLAN 2 devices, which implemented 802.11 DSSS standard. So WaveLAN is basically a brand name for a family of wireless networking technology, which was sold by AT&T and Lucent Technologies. It was in the market from 1990 until 2000. So WaveLAN laid the important foundation for the formation of IEEE 802.11 working group and the creation of Wi-Fi. So this ARF is a primitive algorithm. Even now, most of the APs which are deployed in practice uses ARF because of its simplicity. Coming to the algorithm, in ARF, sender attempts to use higher transmission rate after fixed number of successful transmissions and switches back to a lower rate after 1 or 2 consecutive failures. This means, say now currently the transmitter is sending at rate MCS CM. It can be 0, 1, whatever. After say number of successful transmissions, say it is set to 10. So this transmitter will get to know whether this packet which is being transmitted is decoded successfully at the receiver or not through the acknowledgements. If the transmitter gets 10 successive acknowledgements, positive acknowledgements, then the sender will transmit the next packet with an MCS M+1. If previously, if the MCS was say 1, after 10 successful transmissions, then MCS will be increased by 1. That now for the 11th packet, MCS will be 3. Okay, from 2 to MCS will be 3. It will be increased by 1 rate. And when will the rate decrease? If it sees 2 consecutive failures at any packet number, once it has increased, say from 2 to 3 after 10 successful transmissions, say after a few packets, say after 5 packets, packet is failed. Again, 6th packet also say packet failed after increase in the MCS from 2 to 3. If there are 2 consecutive failures, then the MCS again go back to the switches. The MCS is going to reduce by 1. That is, it from 3 it becomes 2. So the original ARF algorithm actually decreases the current rate and starts a timer. Whenever 2 consecutive transmission fail in a row, when either the timer expires or the number of successfully received per packet acknowledges reaches 10, then the transmission rate is increased to a higher rate and the timer is reset. And whenever the MC rate is increased, say after 10 successful transmission, I told MCS is increased by 1, right? Or whenever the rate is increased, the first transmission after the rate increase is generally called a probing packet, because now you have because you have got 10 successful acknowledgements, positive acknowledgements, you are thinking, okay, channel is good, let me send at a higher rate. So this is kind of testing. You don't know whether the channel is whether the increased MCS will be able to pass through the channel and it it will be decoded at the receiver correctly. So you don't know without knowing the actual channel condition. Because you have got 10 successful transmissions, you're increasing the MCS by 1. So that 11th packet, whatever it is called as probing packet, and if that probing packet fails, what you do, you again immediately decrease the rate or decrease the MCS by 1, and the timer is restarted rather than trying to the higher rate at a second time. So in short, what is ARF? In ARF algorithm, basically it's a implicit feedback algorithm. We call it as implicit feedback because there is no explicit feedback from the receiver to the transmitter about the channel state information. So the algorithm basically depends upon the acknowledgement feedback. And if it sees 10 consecutive positive acknowledgement, the MCS is increased by 1. And if the immediate packet, that the probing packet, if it fails, again MCS decreases by 1. And during transmission window, anytime if there are 2 consecutive failures, then again MCS decreases by 1. So this is the crux of the algorithm. So same thing is depicted in this figure. So in this y-axis is MCS. This you can think as packet number. So if there are 10 successful transmission, MCS increased. So 11th packet, MCS is 2. Again 10 successful transmission. Again after that is 21st packet, MCS increased to 3 from 2 to 3. Then what happens after 10 successful transmission? Again MCS is increased after 10 successful transmission. But the channel is not that good enough to support this higher order MCS. Hence the packet failed. Immediately for the next packet, MCS is decreased. This continues. So from the figure only, it's clear that after every 10 successful transmission, it is trying to increase the MCS by 1. But actually, the true channel is not that good, or the SNR of the true channel and the receiver is not that good to support MCS4. But this knowledge is not known to the algorithm, because algorithm just relies on the fact that after 10 successful transmissions, okay, I'll increase the MCS. So because of this, after every 10 successful transmission, it is trying to increase the MCS, and the packet fails and MCS is decreased. So because of this, you will have more number of retransmissions, and hence it affects the application level throughput. So this scheme suffers basically from 2 problems. If the channel changes very quickly, it cannot adapt effectively. This is by design, because the algorithm waits for 10 packets, then only tries to increase MCS. So even when the channel is varying quickly, and if the SNR is increased, it may not quickly adapt to the increased channel SNR or channel condition. For example, in an ad hoc network, and also when there is an interference, burst of packet errors, that time also, like yeah, for 2 continuous errors, it will decrease this MCS. But whenever the channel changes from bad to good state, it takes some time to sense channel condition. And if the channel conditions do not change at all, so this is that example, it's varying very slowly. Channel condition is not changing, but still it will try to increase the MCS for every 10 packets, and hence decreases application level throughput. And also one more thing is ARF cannot estimate the sub-packet channel condition changes. So this is one result which is given in this paper. If you want to read more on ARF, you can refer to this paper, and also other references are also there. So in this figure, the sinusoidal, the variation of the SNR at the receiver is assumed to be sinusoidal. This dotted line, this is the SNR at the receiver. The circle point indicates the successful data frame transmission. The cross point indicates erroneous transmission. So again, from this figure, we can try to understand what is happening in the ARF algorithm. So 10 successful packets. So it is increasing, but the packet failed. So immediately it came back to the original MCS. Again, after 10 successful transmission, it increased, but now the channel is good. Okay, it's able to send higher MCS. But if you notice, there are 2 X mark here, meaning 2 packet failed. Hence, it immediately decreases the MCS. And after 10 successful transmission, it tried to again increase MCS. Packet failed. time required for the transmission of packet is smaller. This is one thing to note. So these are the additional references where you can refer to know more on ARF. So most of my content in the slide is taken from the reference number 2. So now I think we are good to go to the program. So this as basically this is the main program. This is the function which is written, basically does the packet processing, and this is the code which actually does the ARF algorithm. The scenario basic is again the SNR walk. This we have discussed in experiment 5, the previous experiment, but I'll go through it. So here we create HEMU configuration object. That is, it creates a multi-user high efficiency format configuration object. So here it accepts a parameter called allocation index. So allocation index I have set it to 192. So show allocation will show what is the allocation given with for this allocation index. If you see, the only one user is occupying entire 242, 242 subcarriers. The bandwidth is 2 megahertz, having 256 subcarriers, but the occupied subcarriers are 242, leaving this null subcarriers, DC subcarrier, the guard subcarriers. So all 242 subcarrier is occupied by the single user. Actually, it is an OFDMA mode, but single user is occupying the entire bandwidth. Then you can also obtain the allocation information here, display allocation information. Yeah, it's already displayed. You have one users, only one RU. RU index is 1, RU index is 1, RU size is 242. The number of users per RU is 1. The data payload length is set to 500 bytes. Initial MCS I have set it to 0. Here you can notice something additional, dot user 1, meaning you have only one user, one referring to user index. So if it was a single user, you would have seen CFG SU is dot web length is equal to 500. Because you have multiple users now, you need to change the variable or give the inputs for different users. Otherwise, if you don't give, it would take some default value. So the user 1, I am setting MCS as 0. The number of packets which I'm going to simulate is 2000. I'm going to obtaining the sampling rate. This part of the code just gives the packet duration for different MCS combination. That is MCS varying from 0 to 9. So MCS 0 is 1.12 milliseconds. MCS 1 is 0.848 milliseconds. This I'm computing now and passing it to the function because I need this when I calculate the throughput. So in order to calculate the packet duration for all possible MCS, I'm inside the for loop, I am setting MCS for this first user varying from 0 to 9. From the MATLAB, the index in the MATLAB index starts from 1. But MCS in 11AX for 20 megahertz, MCS support is 0 to 9. So I'm simply changing this MCS from 0 to 9 for I equal to 1 to 10. MCS is set as I minus 1. Here PSDU length I'm obtaining. Then the data bits I'm generating based on the PSDU length. Waveform, WLAN waveform generator generates OFDM modulated symbols with the idle time of 5 exponential minus 4 seconds. Then I'm calculating the duration using the sampling rate and computing the packet duration. So then it displays the packet duration in milliseconds. This is because I'm dividing by 1 exponential 3 so that I get the duration in milliseconds. Then I'm resetting the initial MCS of user 1 to 0 because I'm going to do rate adaptation. To start with, I assume, okay, MCS is 0. Then channel configuration is done. Modality delay profile is used. CISO case and distance is 10 meters. So it is an LOS mode of propagation. Sampling rate is set. Then the path gains, this and all is required. So I've set it to true in order to compute the channel impulse response. Then the random stream, this I've explained about the 2 types of random stream. That is, one is empty 199937 AR with seed, and other default is global stream. When you set this to this, you need to set the seed value. So you want to know more on this random stream, please refer to the previous experiment 5, where I have explained in detail what is the difference between the random stream when set to this and when the random stream is default, that is a global stream. Please refer to the experiment number 5. Then this scenario basic is a small function, which is again similar to the previous experiment, where it that defines the SNR walk. Yes. So again, this also have explained in detail in the experiment 5, the previous experiment, that is a dynamic rate adaptation algorithm or dynamic rate control algorithm. So in scenario basic, they have explained this again, this walk SNR, if it is true, I'm actually changing the SNR following the sinusoidal. What we saw in this example, for example, in this paper, even they have taken the SNR as something sinusoidal. So similar to that, the SNR walk, the actual values taken by this depends upon the mean SNR and the amplitude. You can control this. If you set the mean SNR value to lower, and if you increase the amplitude, maybe the variation is more. So it all the way what should be the range of SNR. If you're looking for good channel, then main SNR should be good enough, should be good. And if you want to simulate or emulate poor channel, then you have to set mean SNR to a lower value and also to amplitude to the lower value. So accordingly, the SNR will change. And if this walk SNR is false, then simply SNR walk is constant 25 dB, and all the variability in the SNR comes from the slowly varying 11x channel. So this I have plotted how SNR walk look like. Yes, this is the SNR walk which is simulated, and this is given as an input to the function. So the function which I'm calling is experiment 6 function, which takes number of packets, this SWU, SNR walk, CFGFU, MU configuration system object, and then the JX channel characteristics to know the channel properties. Coming to the function, it will output the what is the overall data rate when you simulate 2000 packets, what is the overall PR, and what is the MCS which is being used for every packet, and PR store, meaning whether the packet is successful or failure, and the packet duration which is used for every packet based on the MCS. So this packet duration obviously depends upon the MCS used. Lower MCS meaning more time, higher order MCS means reduced time. Okay, coming to the coming to this function, yeah, this uses again one more object called rate adaptation ARF1, which I'm going to explain here. This basically this program is basically the ARF rate adaptation algorithm. This implements rate adaptation algorithm. Let me discuss this first before going to the function. So this rate adaptation, it defines two important parameters, that is a success threshold and failure threshold. Success threshold is set to 10, meaning here after 10 successful transmission, after 10 positive acknowledgement, I told MCS increases by 1, right? So that success threshold is 10. Failure threshold, how many number of consecutive failures will immediately result in decrease in MCS by 1. So that is 2. Whenever there is 2 successive failures, the MCS immediately decreases by 1. And these are some other index parameters, which is private to this privately accessible within this script. What is the current rate index and pre-increment flag. This is very important. This indicates the probe packet. So I told after 10 successful transmission, the MCS is increased by 1, right? So this flag is set to high whenever you are transmitting a probe packet, meaning whenever you are sending a packet with increased MCS after 10 successful transmissions. That is, this flag is set high whenever you are sending a probing packet. This variable counts the consecutive successful transmission. Consecutive failure count also, this counts the consecutive transmission failures. Okay, so these 4 variables are very important. This one keeps the track of what is the current MCS. This is set high whenever the whenever the probing packet is transmitted. This counts the consecutive successful transmissions, and this one counts consecutive or successive transmission failures. Next, coming to this, this is the new rate index. So this increment rate function accepts the hold rate, meaning the current MCS which is used for the current packet transmission, and it computes a new rate and stores it in new rate index. This is output parameter, a new rate index, meaning this is a rate which needs to be used for the next packet. So if the old rate index is equal to 9, meaning if the current packet has used MCS 9, because 20 megahertz supports MCS from 0 to 9 and 9 is a maximum MCS, do not increase the MCS by 1. Simply make new rate index is equal to old rate index. No doubt, SNR may be good enough to transmit higher order MCS. Because 20 megahertz MCS support is from 0 to 9, I am restricting the MCS to 9. And otherwise, if the MCS of the current packet is less than 9, obviously, when MCS is good, increase, like new rate index is equal to old rate index plus 1. And again, when decrement rate, so here increment rate is one more function. We will see when will that increment rate function is called, but what triggers increment rate we are yet to see. But when increment rate function is called, what happens? Simply MCS increases by MCS plus 1, but what the limit is 9. Again, there is a decrement function. We are yet to see what triggers decrement function, but what happens when this is called? The old if the current MCS is 0, MCS will be incremented. If the current index is MCS is 0, the new is same, because you cannot decrease MCS because MCS 0 itself is a lower MCS. Otherwise, new MCS or new rate index is the current rate index minus 1. So we will see when are these two functions called, that is increment rate and decrement rate. First, remember the functionality now. So for this, yeah, this is a function which accepts number of stations. In our case, the receiver station is 1. So this is something which is very internal. And let's go to this. There are two important functions called get rate and update status. Get rate is the rate is output parameter, which is given by this rate adaptation ARF object. And this update status is a function which takes the input from this experiment 6 function. Therefore, this experiment 6 function, I am calling these two functions. So get rate I am calling, okay, and update status I am calling. So, but that has to be called at the appropriate time, so that the functionality of the algorithm is executed properly. So what happens when it is get rate? When it is get rate, simply it will give the rate to be used for the next MCS. Update status, what it does? Update status takes the receive station index is 1 because it is CISO. Is fail is the input parameter to this function, whether the transmission is failure or transmission is successful. Is fail, if it is true, meaning yes, the current packet transmission is failure. If it is false, meaning else, go to else, meaning it is successful transmission. So let's go to this thing, else case, meaning is fail is 0. So meaning implies the packet is successful. In that case, what happens? I told you there is a counter, that is consecutive success count, that will be increased by 1 because the packet is successful. Then the consecutive failure count will be reset to 0. And again, it compared. There are two cases now. Yes, whatever the current, whatever the MCS used for the current packet is successful. So the two cases. First thing is, it will check whether the consecutive success found is greater than or equal to object success threshold. And yes, if it is, then first thing what it does is it will it will increment the rate, right? That's why it is calling increment rate. So increment rate is going to increment the rate. Then second thing what it does is the previous increment flag, what I told, this flag is set high only when for the probing packet transmission, right? So this is set to true. So it will, whenever the packet is successful, it will see whether number of consecutive success count is greater than or equal to 10. If it is, increment the rate and set the previous increment flag equal to true, indicating it is a probing packet. The second case is what? Whenever it fails. When it fails, what happens? When it fails, yes, when it fails, consecutive failure count is incremented by 1. the consecutive success count is set to 0, and it will see whether the previous increment flag is set to high. If it is, immediately it decrements the rate because it is a probing packet which was transmitted is failed. So decrease the rate, then consecutive failure count is reset to 0, and the previous increment flag is also reset to false. Second case, the probing packet may not be failed. Say in between transmission window, some other packet has failed. In that case, if it is not the probing packet, it comes to this and it will check whether it has crossed that threshold, failure threshold, which is 2. Okay, if it is greater or equal to this. If it is greater, then only it will decrement. If not, what? It will wait. For if the one packet is failed, it will not decrement immediately. If 2 consecutive failures happen, then only the decrement rate happens. So if it is greater or equal to 2, failure threshold being equal to 2, then decrement rate happens, then consecutive failure count set is set to 0. So this script does the rate adaptation algorithm. I think this is clear. Basically, you're setting these two parameters, success threshold, failure threshold, and these are the variables which is holding what is the rate index value, what is the probing, whether the packet transmission is probing or not. It counts a successive count. It will have the pre-failure count, and this is for increasing and decrementing the rate. 2 cases whenever the failure happens, and only 1 case whenever success happens. Success, that is simply counts whether it is greater than or equal to success threshold. So this essentially performs the ARF rate adaptation. So coming to the function, how it is being used. I told you basically this function or this ARF needs 2 things. First thing, what is the current status of the packet, whether it is successful or failure. That input it needs. After that, after it does some processing, algorithm is computed. What is the output it is giving? It is giving the rate. So these 2 things must be called appropriately in the function. So here simulation variables are initialized, SNR measured. SNR measured. Keep in mind SNR, the algorithm does not depend on the SNR at the receiver. I am simply calculating it for the sake of displaying the results and just for visualization. So, but SNR measured is not a part of rate adaptation algorithm. So these are all initialized, MCS, packet length, packet duration, etc. Here PSD, TX PSDU is generated, again bits are generated, then it uses WLAN waveform generator to generate the OFDM waveform, OFDM modulated waveform. So this is after performing IF50 and also cyclic preface, everything is added. So you have TXMU wave now, and the current MCS value is stored in the MCS of num packet. Then for receiver processing, the function process packet is called. So process packet take in TXPSDU, TXMU wave, the SNR walk, TJX channel, CFGHU, MU, num packets, ARF algo, etc. Then going to this function. Yeah, it computes the path filter, channel information. Then these are the values that are initialized. Beginning it is initialized to null vector. This is because for every packet it is computed. So that's why this process packet is being called for every packet, and these parameters are computed for every packet. That is why it is initialized to null array. Then this num length of CFGMU is like the number of multi-users. So here num length will give you 1. You can check this because I've used 242 as the RO allocation index. Okay, this is, I'm not able to get the value because this is inside the function. And then, yeah, now the TXMU wave is passed through the fading channel. This RXMU wave is faded signal. Again, AWGN is created using the com.awgn channel, and I am passing the SNR walk, and then this faded signal, when it is passed through the AWGN channel system object, whatever I have, this is the faded plus noise is added to this. We know what is in. It gives the index values for the different fields of the packet. One thing to note, I think in single user we saw HE sig B was 0 because this HE sig B is present only for MU transmission. So if you remember this in experiment 3, we had seen different packet formats. So if you see here, HE sig B is not there even in SU, extended range SU, but HE sig B is present only in HEMU. So in the first or second experiment, you would have seen HE sig B was 0, but here HE sig B is non-zero because it is HEMU transmission. And here again it does symbol timing recovery. This we again had explained. Some of it would be repetition. So perfect timing offset is done. So symbol timing recovery is done using helper perfect uh, timing estimate. So the perfect timing estimate takes in it will actually reconstruct the channel impulse response from the channel path gains. Hence you have HELTF path gains as the input. And also the path filters. This functions returns the estimated timing offset in the variable called packet offset. And this is in samples. And this is done using the channel impulse response. And this is the integer number of samples related to the first sample of the channel impulse response reconstructed from the path gains and the path filters. So first symbol timing recovery is done. Then packet detection is done. For packet detection, if you see the time, this time domain samples equivalent to 4 OFDM symbols immediately following the LLTF are used to determine the HE packet format. So that corresponds to, so after LLTF, if you see here, HEMU format, yes. So LSIG is one OFDM symbol, RLSIG is one more OFDM symbol, HECGA is 8 microseconds, so this is 2 OFDM symbols. So for packet detection, LSIG, RLSIG and HECGA, all these 3 fields are used for packet detection. But before packet detection, one has to demodulate the LLTF fields in order to get the channel on the noise estimates. So this packet offset, we got it from symbol time recovery. So the packet offset is used in order to extract the LLTF. So RX is a received waveform. So RX wave, I would have put RX equal to RX wave somewhere. Yeah, RX is equal to RX MU wave. So using that packet offset, I'm correcting for the symbol timing, and I'm extracting the LLTF field from the received time domain OFDM waveform. Then do the channel estimation. So WLAN LLTF demodulate you do first. So WLAN LLTF demodulate, what it gives a frequency domain. So frequency domain signal corresponding to the LLTF. So whatever is incoming after IFFT, the time domain signal you are transmitting, and the channel input is again time domain. The output of the channel is time domain, and again you need to perform FFT at the receiver end in order to get the frequency domain signal corresponding to the LLTF. So RX LLTF is given. So LLTF demod is the frequency domain corresponding to LLTF. And then you do channel estimation, right? So and also you use the you get the noise variance estimate using the helper noise estimate. If you want to read more in detail, you can just open this particular functions and go through. And also there will be some examples and detailed comments would be given so that you understand the things better. So some of the things I think we have already seen in the previous experiment also. So LLTF is a legacy part of the packet preamble. If you see here, LLTF. So this channel estimation is done in order to decode the pre-HE part of the packet. So this LLTF is used to demodulate LSIG, RLSIG, etc. And HELTF is used to demodulate the HE data field, or whenever there is I mean the receiver is moving. And the standard also supports the midumble, that is HELTF, which is present between the user payloads, that can be used for the channel estimation during the propagation of PPDU itself, right? So this LLTF field, I told you, this LLTF is actually the BPSK modulated pilot symbols. It takes either value plus or minus 1. So when you do channel estimation, it is a simple concept. We know y is equal to hx plus n at the receiver, that is in frequency domain. Y of k is equal to h of k into x of k plus n of k. Ignoring noise, say y of k is equal to h of k into x of k. So uh, we know x of k is the pilot symbols, which is BPSK modulated LLTF. Either it takes value plus or minus 1. Y of k is what? The demodulated LLTF. So this is the y of k, this LLTF demod, I'm calling it as y of k. So how do you get the channel estimates? H hat is simply y. H hat of k is equal to y of k by x of k. X of k is known. Y of k is something which is obtained at the receiver. So get the channel estimate. So again, using LLTF demodulate, the noise estimation is also done. Then packet format detection is done using these channel estimates and the noise variance. And the field which is used is LSIG up to HECG. That is the 4 OFDM symbols following LLTF. That means LSIG, RLSIG, HECG. All this is given as the input in order to compute the, in order to find the packet format. So the packet format can be like HT, non-HT, HESU, HEMU. These are the possible output for the packet format. So more on this, again, you can refer to the WLAN PPDU structure. So non-HT, all these versions of 11 802.11 is non-HT. Again, 11AC is VHT, 11AX is HE. So this particular function, that is WLAN format detect when RxGA, that is when these field formats are given as an input. It can, the packet format can be non-HT, HTMF, VHT, HESU, HEMU, or also HE trigger based. That can also be possible. So after packet detection, then it decoding of all individual fields are done. So after packet detection, it decodes what is LSIG, RLSIG decoding. So LSIG decoding, RLSIG decoding, HECG decoding, sorry, this one, HEMU, HECG decoding, HTSTF decoding. So all of this happens in the next part of the code. So LSIG decoding, RLSIG decoding. So for decoding, what do you use? You use packet offset. This was, you got, it's a variable which tells the symbol timing offset. So if you want, before extracting that particular portion, you'll have to consider this. Use HED modulate for decoding the LSIG. So here the field should be given. I mean, this is the input waveform, and which field you need to specify, and also you need to specify the channel bandwidth. Then you do common phase error tracking. You do channel estimates again on the pilot subcarriers. Then you will do HECG decoding. Again, you will do use the same function W and HE demodulate, but you specify which field has to be decoded. Then you do HECG decoding. Then comes HE data decoding. So this part of the code, in order to write this part of the code, I have referred the example program. There is one more example program, recovery procedure for 11AX. So this was very helpful for me, this particular example program, in order to write the code for on my own. So this explains how what are the steps to be done for the recovery procedure for 11AX packet at the receiver, and in detail everything is explained. So if you are interested, please refer to this example. So here the section of the each section of the MATLAB code is explained in detail. The steps are also mentioned in detail. We saw the front-end processing, what happens, and the packet format detection, the channel estimate, the LSIG, RLSIG decoding, and HECG decoding, HECG decoding, everything. So until this, I have referred to this example in order to write the code. So please refer to that example. So all this decoding has to be passed. Only then the packet is going to be processed further in order to decode the HE data. If any one of the detection of any field in the packet fails, then it displays the error telling that HECG CRC failed for all users, meaning because I'm using OFDM mode. So if HE some other part fails, then again it displays error. So for doing HE data decoding, all these fields must be decoded correctly. Then only it will go for HE data decoding. So coming back to the code. So number of users, in our case, it is 1. So HELTF demodulation happens for channel estimation. HELTF in HUMU is actually variable. You can set it. I have not explicitly set, maybe take some default values. It has again 3 possible combination for HELTF. Then double and HE demodulates. So HELTF demodulate, you have your frequency domain representation for HELTF. Then HELTF channel estimate, this has the channel estimates on 242 occupied subcarriers. So LLTF channel estimate length was 52, but channel estimation when done using HELTF fields, this channel est length is 242. That is H of K for K varying from 1 to 242. Then you demodulate the data, then do the equalization, and more importantly, compute the SNR. So here the channel power includes both the noise and signal power, which is computed using this channel estimates. And then I'm finding the SNR. Okay, here whenever the SNR is less than -10, whenever the channel power is greater than noise power, I'm setting it as -10. This is because otherwise MATLAB will display some error and the program will not run. What I want to tell is, like, anyhow, I'm not using SNR in the code. Even if I use, if the SNR is very low, if it is too negative, the only one option left with me is use MCS 0. But in this algorithm, anyhow, the MCS chosen is not dependent on estimated SNR. But if your logic is such that the algorithm do depend on the measured SNR, then you can set all the negative values of SNR to something -10, -5, anything. And whenever SNR is less than 0, you can set, whenever SNR is negative, you can choose the rate MCS is equal to 0, that is BPSK, which is the most robust MCS. Here, this we have discussed again. The transmit BSDU is compared with RxDU. The packet error is stored in PR store. And here, yeah, this is the time when update status is called. So update status, this number of receive station is 1. This is the object, error of algo. The packet error. Packet error is either now 1 or 0, whether TX BSDU equal to RX BSDU or not. So this information is sent. So if you see update status, when is it required? Yeah. So to check whether the transmission is success or failure, so it is collected in is fail. This is update status is sent here. Packet error is sent as an input parameter. Then get rate is again used at the later point of time. We'll see when is that. So now end function is done. So that is the process function is completed. After processing the packet, what are the computed SNR you are storing it? You're computing the packet duration, and you're computing the bit error rate. Then here, the get rate. Get rate function was giving what is the new MCS rate that is collected in new rate, and then it is new rate is given to the CFG HEMU.user1.MCS, so that this MCS will be used for the next packet transmission. Now you're displaying the packet error. This we have discussed. This is the total number of packets. This gives the number of successful packets, and hence throughput is calculated. The sum of packet length is a time required for the transmission of all 2000 packets. 1 exponential 6 is divided, so the throughput is expressed in oral data rate is expressed in megabits per second, and this gives the number of packets in error. So in order to find the PR, and at the end we are plotting the results. So MCS SNR measured, this is just for reference. The BR plot is also there. BR means instantaneous BR for every packet, and the window length is set to 10 here. The data rate, move data rate. Again, if you want to know more on this detail, you can refer to the previous experiment, that is experiment number 5. So now seeing the result, we have throughput plot MCS. You can see After every 10 packet, as MCS is increased by 1. Actually, the channel was good, but ARF, it cannot instantaneously sense the channel and set the optimal MCS. Hence, it takes some time. So after 10 MCS, MCS is increased by 1. After 10 successful transmission, again MCS is increased by 1. So there is some amount of delay. After 91, after 90 packets, actually it is able to sense, yes, the channel is SNR is good, and it has set the MCS to the maximum, that is 9. And then based on the number of facts or NACs, the MCS is varied accordingly. And you can see the throughput is dependent on the MCS chosen. Whenever the channel is poor, the throughput is decreases, or whenever there is a packet failure, again the throughput is decreased. So the better explanation would be using this plot, because there are large number of packets. I'm not able to explain it clearly. Okay, considering only 200 packets, if you can see here, after 10 successful transmission, the probe packet, this is the probe packet, it failed. So immediately MCS is decreased. Okay, maybe here there are 2 receptions failure. So again, packet is decreased. Again, packet is increased. The probe packet, if it is failed, decreases. So whenever you see something like this, it means the probe packet is failed. So immediately the MCS is decreased. Here there are 2 successful reception failure, hence the MCS is decreased. So this is the ARF algorithm. Here you can, one thing what you can do is in SNR walk, as I told you, you can vary these parameters and see how algorithm performs. And in the command window, yeah, I do have some results. It displays what is the overall date of ARF. It is 6.1697 Mbps, and the PER, packet error rate, is 0.04. And this is the time taken for the transmission of all 2000 packets. Yes, this is what I had to tell for this particular experiment. You can change parameters and see how the algorithm performs. For example, you can increase the distance here. Here you can change the seed value and see what happens in order to emulate different channel conditions, etc. And one more important thing is you can change this user allocation index. For example, 192 is there, you can change it to 0, 15, etc. I'll tell more on I'll refer to the allocation index. There you can see changing this allocation index. You can run this program, but at the receiver processing, you may have to do the packet processing for every user. That I give you as an assignment, because here decoding is done only for a single user, because in my case it is a single user. But what happens if there are multiple users? Again, you can refer to example. I think this particular example itself had multiple users, maybe 4 users. So you can refer to these examples and try to implement ARF algorithm for FDMA mode of configuration with multiple users. Yeah, here it had used multiple users. You can see how what changes has to be done at the receiver processing. Thank you.